This next lesson is on Lesson 8, Number Sense. We're in the Algebra 1 Mod 1 content. And yes, there's probably some sort of assessment coming up, but a lot of these are going to be intended as a review or as a reminder of things that you should already know. So let's start with the intro task. Put the number 7,654,321 on a place value chart as follows. As in, there are 7 millions, 600,000s, 5, as in 50 thousands, 5 10,000s, 4 thousands, 3 hundreds, 2 tens, and 1 ones. It can be written as millions is a number followed by 6 zeros, so 7 million. 100,000s, 10,000s, 4 thousands, 3 hundreds, 2 tens, which is 20, and then 1. We can also treat this with place value, that this number right here, 2, is in the ones digit, and so things that move after the decimal are considered tenths, but you have a th on the end of it. And I also like to think this as tenths is like 1 divided by 10. And if there's a single 0 in 10, then I need the first digit after the denominator. Hundredths, as in 1 over 100, there's 2 zeros. So I think, what is the number that is 1 space or 2 spaces after the decimal? Thousands, so 1, 2, 3, and 10 thousandths, 1, 2, 3, 4. So 1, 2, 3, 4. It can be written as 2, that's the ones, and then 0.1 or point something, that's tenths, 0.0 something is hundredths, 0.00 something is thousandths, I'm trying to say the th, 0.000 something is 10 thousandths. A little bit of number sense there for you. Let's talk about rounding. And I like to think about how we can round up and down for single digits, but you're going to be rounding up and down for tens, hundreds, or tenths, hundredths in the decimal range as well. So if the number there, if you start at 0 and you count all the way up to 10, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gaps. From 0 to 5, there are 5 gaps. And from 5 to 10, there are 5 gaps. So if you're at 0, you're going to stay at 0 if you round. If you're at 5, you're going to stay at 5 if you round. But if we're talking about do we round up or round down, let's say you're at like 4.9. That will round you down to 0. If you're at 5.1, that will round you up to 10. The question is, what do we do with the 5? And so then we'll be trying to talk about if 5 is the separator of rounding up and rounding down, and we're including 0, all of these numbers round to 0. All of these, 1, 2, 3, 4, 5 of them, they round up. So there are 5 numbers rounding down and 5 numbers rounding up, and it makes the things balanced. 5 is the separator. So if we're going to round the following numbers to 10, 7, 0, 5, 10. 7's in this grouping, so 7 will round up. Carry on. 15, 13 is in this grouping, so 13 will round down. 25, because of the 5, 25 is exactly on the dividing line, and anything that ends in a 5 will round up, or higher than 5. So we can consider this with like single digit numbers, but now that round up to the nearest tens, but now let's round up numbers up to the nearest 100. And so all that I'm going to do is instead of saying 0, 5, 10, I'm going to say 0, 50, 100. If I'm in this interval, like how 76 is, I'm going to round to 100. If I'm in, let's see, 50, if I'm in this interval, like 112 is, I'm going to round down to 100. And then 150 is exactly on the line, but anything 150 and higher rounds up to 200. And I chose this question because you don't have to just estimate by rounding to the nearest 10. You can round up to the nearest 100, and it's the same concept. The 50 or the 5, they kick numbers up to the next highest like whole number. This procedure is the same with decimals. So like 0.5, 0.05, 0.005. So if we're going to round this number to the nearest tenth, think about 0 and 1 and how 0.50 is right there in the middle. 0.85 is in this interval, so 0.85 is going to round up to 1. 1.643, that's like the golden ratio. It is 1.6, and because 6 is higher than 1.5, that means that it will round to the nearest, oh, wait, I need to read this better. Nearest hundredth, that's the 4. Oh my goodness, I almost made a mistake. That's the 4. So the number after the 4 is not higher than 5, so it's going to stay 1.64. Thousandth, that's the third decimal. 1, 2, 3. So I'm focusing on the 4. I'm going to look at the 5. 45, that's how we had that 5 in the middle. So 45 is going to kick up a number. 234.875 is the nearest thousand. Okay. Whole numbers are, well, I'll give you the LeBrandt definition, and you can get something similar by Googling it. Whole numbers are positive, non-fraction numbers. Now, there's a better term than this, so I'll put a question mark there, but I hope that convinces you that I mean 1, 2, 3, 4, etc. Integers are positive or negative whole numbers. Oh, and 0. Whole numbers like 0, is that a part of it? Probably not. Okay, so examples. Positive 1, negative 1, positive 2, negative 2, etc. Oh, don't forget 0. Okay? Okay. Rational numbers are fractions, and they are made from integers. So I guess technically whole numbers are integers, and integers are fractions, but like this non-fraction, like that's the part where I like had a question about it. But you kind of get the idea. 1, 2, 3, 4, like where's the fraction? So rational numbers are fractions, and they have to be fractions made from integers. You can't have like pi over 2. This is a fraction, but it's not a rational number. Rational numbers like 1 over 2, negative 3 over 4, negative 50 over 25, okay, etc. 0, don't forget 0. 0 can be made into a fraction. Note that 1 over 0, that's not a fraction either. Okay, so please do those two. Like these, I'm going to use a highlighter. I'm so impressed with those. These are great non-examples. They are not fractions, even though they have a fraction bar. Okay, I'm going to continue on. So page 43. Mark the box that describes the given number. 12, it's a whole number. It's also an integer. It's also a rational number. 8, it's a whole number. It's also an integer. It's also a rational number. 0, not a whole number, but it is an integer, and you can therefore make it rational. Same with 18. It is an integer, and therefore it's also a rational number. 6 over 4, that's the same as 1.5, and that's a decimal, so it's not an integer, but it is definitely a rational number. This is a decimal, so it's not a whole number, not an integer. Negative 5 and 73 hundredths, or 5.73, this is a rational number. This 65%, I mean percent, literally means out of 100. So it's a fraction, 65 over 100. And if you can turn this into a fraction like this, not a whole number, not an integer, definitely rational. 6/3, it's rational. But is it rational if you simplify? Oh, yeah, absolutely. True. Because 2 is a rational number. Okay, let's talk about some operations on real numbers like fractions. We've already done some math like this earlier in the trimester, like I think even last trimester, but it's coming back again because it's good stuff. When you multiply, straight across. So 4 times 6 and 5 times 7, straight across. That makes 24 over 35. With this problem, 4/3 divided by 2/5, let's write this as a stacked complex fraction. And I want to do that because this symbol, it smells. It's terrible. All right, so 4/3 over 2/5. And because we have this complex fraction, this is a problem. So stacked fraction, cancel denominator. And the thing I boxed, this is the denominator. So in order to cancel the denominator, we have to use the reciprocal. So that means 5/2, 5/2. The 2's cancel, the 5's cancel. They technically make 1/1, and this is 1, and dividing by 1 is still the same thing. So it's like the 1 doesn't even need to be there. But then we have a rewrite. We have 4/3 times 5/2. It's like this fraction flipped. And here's why. Now, we have a multiply, and when you multiply, you go straight across. So 4 times 5 and 6 times 3 times 2 is 6. Okay, I'm going to pause the video. I'll come back to the problems in a little bit. All right, I'm back, and you never left. Okay, so I'm going to carry on. Still in the bottom of page 43, and we're talking about adding. And in this problem, we have fractions that don't have the same denominator. A couple of ways to find a common denominator. So need a common denom is to look at multiples and find the multiple that's relatively nice to use. So like 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5, 4 times 6, 4 times 7. I guess it carries on. 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 6, 6 times 7. I didn't need to go that far because I guess if I look at it, these are the same number and these are the same number. And because I have multiples that are starting to show up in repetition, that means that I can take this fraction, I can take the 4 and turn it into a 12. Well, to do that, I have to go 4 times 3. So if I multiply 4 times 3, that makes a 12. If I multiply the bottom by 3, I have to multiply the top times 3, which makes 3 times 3. And 5 times 6, in order to take a 6 and turn it into a 12 through multiplication, I have to go 6 times 2. That makes a 12. But if I multiply the bottom fraction by 2, I have to multiply the top fraction by 2 as well. So I have 5 times 2. Bring the plus sign into play. So technically what I have is these are common denominators, so I'm just going to write them as one denominator of a bigger fraction. And 3 times 3, 5 times 2, and we're adding. So with the common denominator, the numerators are now added to make 9 plus 10 over 12. Answer. This problem also is the same for subtraction because addition and subtraction are similar operations. One is the opposite of the other. So if I need a common denominator for adding, I need a common denom for subtraction. So I look at multiples of 8. 8, 16, 24, 32, 40, 48, ... I look at common multiples of 3. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, ... I guess this the easiest way to get a common denominator is just to take those two numbers and multiply them together. Right? When you do that, you get, well, they both have a 24 in their list. There's one and there's one. So therefore, 8 times 3 makes 24. You could have larger denominators, and we could have even done that over here. 4 times 6. 4 times 6 is 24. And I mentioned the 24s. It's just that 12 was smaller. Because of this list, this number is the least common multiple between those two numbers. So 6 eighths, to turn an 8 into a 24, I got to multiply it by 3, which means the top is multiplied by 3. To Turn the bottom. I have 2/3 to turn a 3 into a 24. I got to multiply 1, 2, 3, 4, 5, 6, 7, 8. Right? 3 times 8 is 24. It means I got to multiply the top by 8. So I wind up having 24, and I have on the top 6 times 3, which is 18, and 2 times 8, which is 16. So I really have 2 over 24. That's not reduced. So even and even makes 1 over 12. All right, when you subtract fractions, you need a common denominator. When you add fractions, you need a common denominator. When you compare stacked, when you're dividing, look for a stacked complex fraction where you cancel the denominator by multiplying by the reciprocal. And multiplying, easy peasy, straight across. All right. And, on the back. So when we have operations on rational numbers with decimals, let's do this all by hand. Yeehaw. Okay, so the trick that I remember doing when I was, learning this myself is that I'm going to put the number that has the longer amount of decimals, like 1, 2, 3 decimals versus 1, 2 decimals, and then 5.720. I might also be trying to put the big number on top. Now add 6 plus 0. Wait, where'd the 0? I had to add a 0 here, right? 5 and 72 hundredths. That's tough to say. So 5.72. I add a 0 to the end of it to now make it 720 thousandths. Still tough to say. 5.720. 6 plus 0 is 6. 3 plus 2 is 5. 1 plus 7 is 8. 9 plus 5 is 14. That's using an algorithmic process. There are some mental math ways to do it. This is probably easier to show in the moment. Okay, same question, but this time I'm going to put the 9 on top. I just need to remember that this number is positive and smaller, and this number is negative and bigger. And because I'm subtracting, I'm going to have a negative answer. But I'm going to do the math just like I would if it was written better, more suitable. 4 and 560 thousandths. Subtract. 3 minus 0, 7 minus 6, 8 minus 5, decimal, 9 minus 4. That's a positive answer, but because of this conversation right here, it's a negative answer. I have $4.56, and I need to borrow $9.87 in this ever 3. I need to find or borrow $5 extra. Okay, so multiplying. I saw some of you doing this with other problems, and I appreciated what you were doing. I'm going to use this algorithm process. There are other ways, like with pictures and whatnot, but I think the algorithm might still be memorable. So with the decimals are a problem. I'm going to wait to do any math with the decimals. I'm just going to pretend they're not even there. 4 times 3 is 12. Carry the 1. 3 times 1 plus 1 is 4. 3 times 3 is 9. So 942 is what you get from multiplying 3 times 314. Now the 2 is technically one space over, but that's because it is in the ones digit or the tens digit, and we've already done math with the ones digit. So anytime we have a tens digit, it's like there's a 0 there. So we're really doing the math with 20, but that just really lets me know I need to have a 0. I need to think about how 20 is one extra space that way. Okay, 2 times 4, well, 20 times 4 is 8. 2 times 2 is 1 is 2. 2 times 1 is 2. 2 times 3 is 6. So if I write them all out, remember the 0 for this next number. Now I have 2, add 12, carry the 1, 13, 7. Yay, 7,322. No, that's too big. This number was 3 point something. This number is 2 point something. My answer has to be around 6 point something. So this is the way I know that my answer is right. There's 1, 2, 3 numbers after the decimal. So I start from here and I go 1, 2, 3. That's my answer, 7.322. 7 and 322 thousandths. To divide, I love the process of division. It's very, very formulaic. I start with the, what do they call this? Dividend. So the dividend, put it up here, 2.6. And I have my, notice a long line, I have my divisor, 1.95. And I want my quotient. So in order to get my answer, dividend, divisor, and I want my quotient. Put it like that. Okay, well, mathematically, keeping track of all of these decimals is going to be tough. So why don't we just multiply both numbers by 100? 1.95 times 100. When you do that, you get 195.00. So it's almost like this decimal moved 2 spaces to now make 195. And if you take 2.6 and you multiply by 100, you get 260. So get rid of u, add a 0, put a decimal. That's an important step. That allows us now to be dividing integers and not dividing decimals. We make everything 100 times bigger, or however many decimals we need on this divisor to make it, on this divisor to make it become a whole number. Okay, 195, it doesn't go into 2. 195, it doesn't go into 26. 195, it goes into 160 one time. 1 times 195. Now we're going to take away the difference. So 0 and 5, 0 is not bigger than 5. So I'm going to go 10 minus 5. 6 is not bigger than 10, so 16 minus 10. And 2 minus 2 is 1. Okay, so 65. Now, this is not done. I have 65 and 195 hundredths. I can maybe get a little closer if I put this decimal up here, and then I add a 0 and I drop a 0. There's always zeros to add and drop. Now let's go. 5, 4. This is close to 200, and this is close to 600. So 3. 3 times 5 is 15. Carry the 1. 3 times 9 is 27. 28. Carry the 2. 3 times 1 is 3, plus 2 makes 5. So I have 650 minus 585. So 0 is not bigger than 5, so 10 is minus 5. 5 minus 9, no. 15 minus 9, and 6 minus 6. Oh, I ran into a repeating decimal, 65. 585, 65, 585. We get a repeating decimal, 1.3. Repeating. I'm not going to give a ton of explanation here other than it just keeps going. Turtles all the way down. All right, and finally, the piece de resistance. Not correctly said in French. Anyway, simplifying numerical expressions with GEMDAS. All right, PEMDAS is lame and not even written that way. This is not accurate. It's not helpful enough. But if we think about anything grouping, that's coefficients, that's fraction bars, that's this, parentheses, of course, that's square roots, that's whatever we have option to. That has to happen first. So 2.3 minus 4.3. 4.3 goes first because it's the bigger number. 2.3 goes next. We subtract, we get 2.0, and it's negative. Negative because but it's squared. Minus 5.5 times 4. Okay, so that makes this become a 4. 4 minus 5.5 times 4. What I've done is I've done the groupings. I did the exponents. Now I have to do the multiply and divide. So 5.55 times 4. 4 times 5 is 20. Carry the 2. 4 times 5 is 20. Add the 2. 220. That's not good enough. $5 times $4 is $20. Where this is not close to 20 at all. Oh, wait, there's a decimal. So the decimal starts from the end, goes over one space. 22. This is really 4 minus 22. So we're done with multiply, divide, which are technically the same. Now we're going to do add, subtract. There's only one thing to do. It's subtract. 4 minus 22, negative 18. Okay. Extra practice. All right, checking the next page. Please make sure you do the closing. There is no closing statement other than which is better. I'll make one up right now. GEMDAS or PEMDAS or GEDMASA. Which is better and why? And then rate yourself. I'm going to write that. You're not going to remember the question. Which is better? And why? Okay. Please do the exit ticket. It's a good question. Really, all you're doing is just simplifying what's happening right there and say that it equals t. And, of course, you know it. You need the extra practice. You should do a problem set. All right. Thank you and goodbye.